Think about how a world-class athlete actually learns. I mean, they don't just magically get better overnight, right? They rely on a coach to watch their performance, spot the exact moment they messed up, and guide them on how to fix it. Well, training in artificial intelligence works exactly the same way. Today, we're cracking open the coach's playbook to demystify the mathematical engine that actually drives machine learning, AI loss functions. But before we get into the heavy lifting of how these playbooks work, we really have to ask a foundational question. How does an AI actually know when it's wrong? Under the hood, an AI is basically just a massive, chaotic web of billions of numbers. Without a strict mechanism to realize it just made a mistake, it absolutely cannot learn. It would literally just spit out random noise forever. And that mechanism is the loss function. It is the primary feedback signal quantifying the discrepancy between a model's prediction and the absolute ground truth. Think of the loss function as the ultimate penalty. It's the steering wheel, forcing the AI to update its parameters. The bigger the discrepancy, the higher the loss. And the AI's entire goal in life, its sole mathematical purpose, is to minimize this number, getting it as close to zero as possible. So here's our roadmap for this explainer. First, we'll look at the AI feedback loop. Then, the specific teaching styles for classification, regression, and ranking. And finally, we'll dive into the modern methods powering today's most advanced systems. All right, let's jump right into part one, the AI feedback loop. It is super fascinating to contrast two very different paradigms of learning here. On one side, we have loss functions, which are entirely rooted in statistical error minimization. It's really a defensive posture, reducing the distance between a prediction and the absolute truth. But contrast that with utility functions, which is a concept from economics focused on preference maximization. That's about chasing a reward. Knowing whether an AI is mathematically programmed to anxiously avoid a penalty or aggressively chase a reward fundamentally changes how it behaves out there in the real world. Moving on to part two, classification, or sorting the world. When an AI's task is classification, it has to definitively sort the world into discrete buckets, deciding if an image is a cat, a dog, or a bird. The mathematical foundation for this is the softmax function. If you look at how probability is distributed across these classes, softmax ensures they always sum up to exactly 100%. By forcing the AI to divide a single pie of probability, giving a super confident 70% slice to cat mathematically forces it to take slices away from dog and bird. But how does the coach actually grade this distribution? Enter categorical cross-entropy loss. This function calculates error using something called negative log likelihood, which is honestly just a fancy way of saying the penalty scales exponentially based on the model's confidence. If the AI is 99% sure an image is a dog, but it's actually a cat, the mathematical penalty doesn't just incrementally increase, it explodes. It teaches the AI a truly vital lesson. Don't just be right, but properly calibrate your confidence so you aren't confidently wrong. This whole idea of cross-entropy actually originates from information theory. And to truly grasp the underlying math, which is a concept called Kullback-Leibler divergence, or KL divergence for short, let's step away from AI for a second. I want to use a brilliant analogy involving two very different boxes of Lego blocks. Imagine the first box. It is totally full of Legos of every color and size imaginable. Drawing the block blindly is highly unpredictable. In information theory, we call that high entropy. Now imagine the second box. It only contains identical yellow bricks. Highly predictable, right? That's low entropy. Now, if your AI is trained to expect the boring predictability of that yellow box, but suddenly you force it to draw from the chaotic mixed box, it's going to be shocked. KL divergence is the actual mathematical measurement of that exact level of surprise. It calculates how much the model's assumed view of the world diverges from true reality. All right, part three, regression or predicting the numbers. When estimating continuous numbers, like tomorrow's exact temperature or the price of a house, our AI coach relies on two classic loss functions. The first is mean squared error, or MSE. MSE strictly punishes large outliers by squaring the error, meaning if you're off by 10, your penalty is suddenly 100. This works beautifully for smooth data, but it is absolutely terrible if your data has crazy, unpredictable anomalies. Contrast that with mean absolute error, or MAE. It treats errors linearly. Off by 10 means a penalty of 10. This makes MAE a massive shield, making it far more robust when your dataset is just full of wild, heavy-tailed noise. So here is exactly what you should take away as a rule of thumb for building these systems. You use MSE when you expect normal, predictable noise, and you use MAE when your data is messy with extreme outliers. But if you want the ultimate coach's trick, you use Huber loss. Huber loss is this incredibly elegant hybrid. It acts exactly like MSE for small errors, giving you smooth optimization, but then smartly transitions to acting like MAE for massive errors, ensuring those wild outliers don't completely wreck your training. Up next, part 4, ranking, learning what's actually better. Sometimes the AI coach needs to act a bit like a matchmaker, focusing purely on the relative order of things rather than giving out absolute scores. And what's mind-blowing here is that ranking losses thrive on what we call weak supervision. Think about Face ID on your phone. To train that system, the AI doesn't need to know your exact name, your age, or an explicit numerical target for your face. It merely needs to know if 2 photos belong to the same person or different people. It is entirely about relative mathematical distance. So let's look at how this builds a precise geometric space using a technique called triplet loss. The coach grabs 3 things simultaneously. First, a baseline anchor sample, say a reference picture of you. Second, a positive sample, a different picture of you. And third, a negative sample, a picture of a total stranger. The underlying math literally acts like gravity and magnetism here. It pulls the matching positive example tightly toward the anchor and violently shoves the mismatched negative example away by a strict predefined margin. It directly carves out this discriminative space where you are clustered perfectly together. Finally, let's dive into part 5, modern methods, covering contrastive learning and reinforcement learning. A massive breakthrough powering today's most advanced systems is the SimCLR loss framework. Historically, AI needed humans to painstakingly label millions of images, which is just incredibly expensive and slow. Well, SimCLR cleverly creates its own labels. By taking just one image and applying a simple color filter or a crop, it generates 2 slightly different views of the exact same thing. That automatically becomes a positive pair. It then treats every single other image in that massive training batch as a negative sample. This brilliantly builds an enormous, label-free learning environment. The AI learns the fundamental visual structure of our world purely by contrasting these augmented images against each other. It literally saves millions of dollars in human labeling costs. Now, what about deep reinforcement learning? In RL, the coach isn't just greeting a single isolated test question like categorizing an image. Instead, they're evaluating a continuous, high-stakes sequence of decisions over time. Think of an autonomous AI trying to navigate a physical maze, or a self-driving car managing a busy intersection, or even a bot trying to beat a complex video game where the reward is totally delayed until the very end. In this space, we've basically got 2 primary loss types. First, Q-value loss. This forces the AI to be consistent with its own future predictions. It calculates the error between the reward it expected to get and what it actually got, using the famous Bellman equation, which basically mathematically links current choices to future payoffs. On the flip side, policy gradient loss doesn't even bother estimating the exact numerical value of a state. It just directly steers the AI's behavior, tweaking the probabilities of specific actions to maximize those sweet, long-term expected rewards. So, to summarize our explainer today, building a capable AI really comes down to selecting the ultimate coach's playbook. The underlying math absolutely must match the task at hand. If your AI is a categorizer, you use cross-entropy for sorting. If it's an estimator, you deploy Huber loss to handle numbers and noise. If it's a matchmaker, triplet loss optimizes those relative rankings. And if you're building an autonomous agent, policy gradients will shape its sequential actions over time. As we wrap up, I want to leave you with this provocative thought. We have spent all this time perfectly engineering loss functions to act as human-designed coaches for our AI. But as these models become increasingly autonomous and vastly more capable, how long until they begin designing their very own loss functions to correct their own behaviors? It is a fascinating and perhaps slightly terrifying frontier for the future of AI alignment. Thank you so much for joining this explainer, and keep learning.